This is about electric potential. The electric potential at every point in the universe will be different. You will have a point A, you will have a point B, which will be at a potential VA, VB due to some source charge. And how do you define the electric potential at any point P? The electric potential at any point P is defined as the amount of work done in bringing a unit positive test charge from infinity to that point against the electrostatic force. Okay, this is known as electric potential, and you all know that is represented by volts is SI unit for electric potential. So every point in this universe has got a unique potential because of the source charge. And supposing you're bringing a 2 coulomb, what is the work done bringing it here means it's this potential multiplied by this 2 coulomb. Because V is equal to W by Q, W is equal to V into Q, you have to take the potential multiply with the charge that you're bringing it. And that will give you the work done. We'll come back to the potential energy of the work done later. So this is what is electric potential. Now you have, let's derive the electric potential formula. You have a source charge which is positive. You're bringing a unit positive test charge from A to B. Against, the electric field is in this direction and you're bringing it along this direction, which is dr. This is at a distance Ra, this is at a distance Rb. Okay, you are trying to find the potential, therefore V is equal to W by Q. From here you have a hint, you have to find work done. Work done itself is F ds cos theta. F itself is E is equal to F by Q, F is equal to E into Q naught. The distance is dr into cos 180 is dW. Cos 180 is minus 1, so dW is equal to minus E Q naught into dr. Bring the Q naught down, dW by Q naught is equal to minus E into dr. This itself is dV, potential V is equal to W by Q, so it will become dV is equal to minus E into dr. Therefore, E is equal to minus dV by dr. This is the formula. E is equal to minus, that shows that electric field is a negative of potential gradient. The SI unit can also be volt per meter. E is equal to F by Q, which is Newton per coulomb, but this is also volt per meter. Okay, from here you can diversify this derivation and go in another route where you can write E as 1 by 4 pi epsilon naught into Q by R square into dr. Integrating both sides, integration of 1 by R square is minus 1 by R. This will become V minus 1 by 4 pi epsilon naught into Q into minus 1 by R. Integrate from Ra to Rb. Negative of negative will become positive, so it will become 1 by 4 pi epsilon naught into Q into upper limit minus lower limit Rb minus Ra. If you take LCM, you will get Ra minus Rb, and Ra is greater. Therefore, the potential will be positive if the source charge is positive. So, if supposing this A is at infinity and B is some R, the whole formula will change as 1 by 4 pi epsilon naught into Q by R. That is the potential at any point R. That's all. Okay. So, this derivation. Next is this is to derive the potential at any point. This is to prove that electric field is negative of potential gradient. This path is to find the potential at any point R, okay, from a source charge. So let's go to next derivation. Supposing you have a dipole minus Q1 plus Q. The question is to find the potential along axial line or an equatorial line. It's not an electric field for you to resolve vectors. Potential is a scalar. Let's find the potential at any point P, which is at a distance of R from the center. So then therefore, let's call this as A and B. This position vector is RA. This position vector will be RB. This angle is theta. This angle is 180 minus theta. We're going to use law of cosine here, where if you know this is A, this is R and this is theta, you can find the opposite side, which is RB, which is root of A square plus R square minus 2AR cos theta. If you take let's take this triangle where you have an R and an A and you have 180 minus theta, you can find RA. This RA, which is on the opposite side, can be found by A square plus R square minus 2AR cos 180 minus theta. Cos 180 minus theta is minus cos theta, so to become RA is equal to root of A square plus R square plus 2AR cos theta. And RB will be root of A square plus R square minus 2AR cos theta. Okay, now you know that R is much larger than A, and A by R that will become fraction which will be negligible, because A is smaller, R is larger. A square by R square will be even more negligible. Let's get an A square by R square, for which take the R square out. It will become r a square by r square plus 1 plus 2a by r cos theta. And rb itself is root of, if you take an r out, a square by r square plus 1 minus 2a by r cos theta. A square by r square is negligible, cancel. So Ra is equal to r into, the root can be written as whole to the power 1 by 2. And Rb can be written as r into 1 minus 2a by r cos theta whole to the power 1 by 2. This can be brought here by binomial theorem. Okay, 1 plus x the whole to the power n is 1 plus nx. 1 minus x the whole to the power n is 1 minus nx. Using this, the half will come to the center. If it comes shifts here, the 2 and a half will get cancelled. Ra becomes r into 1 plus a by r cos theta, and Rb will become r into 1 minus a by r cos theta. If you take LCM now, r and r will get cancelled. R plus a cos theta, Rb is equal to r minus a cos theta. What is the formula for potential? 1 by 4 pi epsilon q into 1 by Rb minus 1 by Ra. Substituting this, 1 by 4 pi epsilon q into Rb is 1 minus r minus a cos theta minus r by a cos theta. Like this, you substitute Ra and Rb. So 1 by 4 pi epsilon naught into q into LCM is r square minus a square cos square theta, r plus a cos theta minus r plus a cos theta. R and r get cancelled, you get a 2a cos theta. 1 by 4 pi epsilon q into 2a cos theta by r square minus a square cos square theta is what is the potential. This is the formula for potential at any point. Along the axial line, theta is equal to 0. Cos 0 is 1. So 1 by 4 pi epsilon naught into q into 2a can be written as p. This simply we can write this as kp cos theta by r square minus a square cos square theta for any point. And for axial, you can write theta is equal to 0. So kp by r square minus a square. And for equatorial, theta will be 90. Theta will be 90, and so potential along an equatorial line of a dipole, the potential is always 0. They'll ask you, supposing what happens when you're moving a 2 coulomb from here to here. No work need to be done. V is equal to W by Q. So work done is V into Q. Potential itself is 0. The work done is 0. Without doing any work, you can move any charge along an equatorial line. Okay, so then that's the next thing. And next is, supposing you have a hollow sphere. You have an hollow sphere. You are trying to find the potential at any point P due to this hollow sphere which has got charge Q on its surface. So obviously the potential at any point P will be, the formula, V is equal to 1 by 4 pi epsilon naught into Q by R, that's all. At any point P, which is a distance of small r, will be 1 by 4 pi epsilon Q by R. Supposing the question is about interior to the sphere, hollow sphere, interior. Electric field interior is 0 and E is equal to minus dV by dr, it's a negative of potential gradient. If the electric field itself is 0, a differentiation of only a constant can be 0, therefore the potential is always a constant. Therefore this inside it, the potential is always a constant, it's known as equipotential surface. Thus that you can do this graph between a potential and a position vector, and this is small r is equal to capital R. This is when small r is lesser than capital R. This is when small r is greater than capital R. That interior, it is a constant, and after small r is equal to capital R, it's going to be inversely proportional to R. This is where V is inversely proportional to R, and this is where V is always a constant. Okay, so as long as it's inside, it's going to have the constant value. Okay, let's go to next. And you also understood this graph is a must. That electric field is 1 by 4 pi epsilon naught into Q by R square. Potential is 1 by 4 pi epsilon naught into Q by R. I'm going to do a graph which is between E, V and an R. Okay, so then for that you have to do it like this. Let's call this point as 1. Let's call this as half. Let's call this as 2. You substitute a half here in R square. 1 by 2, the whole square will be 1 by 4. The electric field will be 4 times. And here if you substitute 1 by 2, will go up, it will be only 2 times. So then electric field value is greater than the potential's value. So let me put electric field here and the potential to be here, which corresponds to half. This is my V. But when it comes to 1, you substitute 1 here and 1 here, electric E is equal to V at 1. So at some point E becomes equal to V. But when it is 2, substitute 2 here, it becomes 4. Substitute 2 here, it becomes 2. 1 by 4 will have a greater electric field. The 4 is more, it will have lesser electric field. 4 is more, so it will have lesser electric field. The voltage will be more. So as you come down to 2, you will have lesser electric field. The purple color electric field is lesser, while the potential is greater. Corresponds to 2. So when I do this graph, the purple color E goes like this and goes like this. And the potential graph, the green color, goes like this and goes like this. This is the graph, very clear. But this is your potential. Green is your potential graph and E is your electric field graph versus R. Okay. So very, very important. The next thing that I have to teach you is about equipotential surface. The points around a charge which are at the same, all the points which are at the same potential. The surface joining all points which are the same potential is known as equipotential surface. So the surface which has the same potential at every point can be termed as equipotential surface. Let's draw some equipotential surface. So supposing you have a positive charge. Let's draw an electric field like this, electric field line. The equipotential surface will be concentric spheres around it. And weaker the electric field, it will be far away. The equipotential surface density, degree of closeness will be lesser towards the weaker electric field, and degree of closeness will be more where the electric field is stronger for a equipotential surface. And can you see the equipotential surface therefore is perpendicular to the electric field lines. Okay, so then that's one diagram. The second diagram is between a positive charge and a negative charge. Let's draw the electric field line first. Positive to negative, emanate from positive to negative, emanate from positive, emanate from positive, terminate in negative, terminate in negative. And so you're going to do a Gaussian surface here. It will be between positive and negative, it has to be closer. So then it has to be closer, far away, closer, far away, closer, far away. You have to do concentric spheres like this. Closer, far away, closer, far away, closer, and far away. This is how you draw concentric spheres between positive and negative. Between a positive and a positive. The third one is between a positive and a positive. It has to be far away in between and closer outside. It has to be closer here but far away here. Closer, far away. Close, okay, you understood. So it has to be closer outside, far away here. Closer, far away. And it will result in a dumbbell like structure like this. So this is very important. Okay, outside it should be closer and interior it should be spaced out, and this is the diagram. You can see SL aurora for it. The fourth one is supposing you have a uniform electric field. How will the equipotential surface be? It will be a plane A, plane B. This will have one potential, this will have another potential. So the charge particle, for moving from this to this, you don't need to do any work. But if you're moving from here to here, because they are different potential, you may have to do work. Okay, so that's about the equipotential surface for a uniform electric field. And what are the properties? As you can see, the equipotential surface is always normal to the electric field line. And equipotential surface is it's closer where the electric field is stronger, and it's far away. It's spaced out at a greater distance where the electric field is lesser. No equipotential surface can cross each other. If it does, it indicates two directions at one point, which is not possible. The work done in moving a charged particle on equipotential surface is always zero. These are all the properties. I am not writing the properties, but please make sure you are noting down the properties. Okay. So let's go to next is electric potential energy. Electric potential energy. They'll ask you what is the work done in bringing a 2 coulomb of charge to this point. You have a potential at this point, which is basically 1 by 4 pi epsilon naught due to source charge by R. You multiply it with this 2 coulomb. So V into Q. V is equal to W by Q. So W is equal to V into Q. So then therefore the potential energy's formula is 1 by 4 pi epsilon naught into Q1 Q2 by R. So let's summarize all these formulas. F is equal to 1 by 4 pi epsilon naught into Q1 Q2 by R square. E is equal to 1 by 4 pi epsilon naught into Q by R square. V is equal to 1 by 4 pi epsilon naught into Q by R. The potential energy's formula is 1 by 4 pi epsilon naught into Q1 Q2 by R. This is a vector, so you have an r cap. It's a vector, so you have an r cap. It's not, it's a scalar, potential energy, potential, or just a scalar, so it's not a vector. Okay, so this completes the entire summary of what I took. I have to still do some numericals, which I'll do as a separate video when I teach you.